Hello, and welcome to a presentation on variable length subnet masking, or VLSM. This will be an example where the fourth octet of an IP address is split, where part of it belongs to the networking address and part of it belongs to host ID. My name is Dave Seamus. I'm a professor over at Pierce College in the Los Angeles area, and I hope you enjoy the presentation. On our agenda, there are several tasks necessary to actually create a variable length subnet type of internetwork from multiple networks or subnets. First off, you have to understand how many IP addresses or network size that you need in each of your networks. Then you'll want to determine the subnet mask for each of those networks. And you'll do that, of course, for each and every one of the individual networks that make up your internetwork environment. But perhaps in no uncertain terms, the most important thing that you're going to do with that information about the number of IPs needed or the size of each network is to then take that list and sort it with the biggest networks at the top and the smallest networks at the bottom. And then once you do that, then you can go through the task of assigning network addresses to each of those networks. So with that in mind, let's talk about how we calculate what I'm going to call the size of the network. It's really the total number of IPs that are absolutely necessary. And you basically derive that number by counting how many nodes you have in that individual network, and then making sure that you add the two that are reserved for networking and broadcast addresses. Now that count is an IP count, but the size of your network is almost always going to be larger than the IP count because we always have to do two things. Of course, I mentioned one of those, adding the network and broadcast addresses. But the other is network sizes are restricted to being an exact power of 2. So 2 to the power of 2 or higher is a restriction that networks have to be sized on binary, what I call a binary boundary. So in a fourth octet, for example, the common binary boundaries for a split octet, 4, 8, 16, 32, 64, and 128. Of course, your fourth octet could have 256 nodes in it, but then it wouldn't be a split octet. The other thing is I don't list 2 to the power of 0 and 2 to the power of 1 because those would only produce one IP address or two IP addresses, and you can't make a network out of that in most situations because you need your network address and broadcast address. Now, real simple, we talked about counting up your nodes, and when you do that, you have to include everything: PCs, printers, switches, router interfaces, and the two reserved, of course. So in my example here, we need a total of 28 IP addresses, 26 for devices on the network and 2 that are reserved. But once again, you cannot size your networks based on the IP count that you need. You have to make sure that your network size is a power of 2 or a binary boundary. So in this case, we're going to round up our network size to be 32, which is the next higher value that's an even power of 2. In this case, 2 to the 5th power, as we see here. So in our sample, we know that we need 32 IP addresses. Now here's the fun part: determining your subnet mask. This is so amazingly simple, I can't believe it. You basically take 256 and subtract the size in terms of total IP account that you need to be on a binary boundary, and that's going to give you your subnet mask. In this case, since we're doing a fourth octet split, that's going to be the value for the subnet mask in the fourth octet. I'm hoping that it's obvious that because we have less than 256 addresses, that the mask for octets 1, 2, and 3 is 255 because those octets identify a network ID rather than host ID. So I'm going to take a scenario. You work for a company where you're the regional IT manager, and your boss has given you a chunk of addresses, sometimes what we call an address space or an address block. And you have a total of 6 networks. You have 3 local area networks, and you have 3 point-to-point wide area networks that you're responsible for assigning the IP addresses. Now, I want to talk a little bit about the 10.1.1.0/24. The /24 is what we call CIDR or CIDR notation, and it tells us how many binary ones. In this case, because we're referring to an address block, the binary one count is the total number of binary ones in this address that you must not, under any circumstance, change. What that means in this case is you're not allowed to do anything with the first 3 octets. They have to stay the same the entire time that you do your addressing on your 6 networks. So let's take a look at the topology. As we see here, I've got 3 local area networks, LAN A being the biggest, LAN C being the second biggest, LAN B being the third, and then the the wide area networks are equally sized, where they need 2 IP addresses for each one for each router, and of course your network and broadcasting address. So let's take a look now at the process of what we do to develop an IP addressing table. But before we do that, I want to talk about the fact that an address block mask is not the subnet mask that you apply to your interfaces. It's a mask that simply defines the size of the block of addresses that you have. So we are not going to put 255.255.255.0 as our subnet mask on any interface at all. Okay, but with this address block, the 10.1.1.0/24, we basically own every IP address from 10.1.1.0 to 10.1.255. Notice, as I said before, the first 3 octets in this example must remain unchanged. So we are not able to use 10.1.2 or 10.1.3 or anything beyond that. Now let's go ahead and take a look at what we're going to do in the process of building our address table. We talked about these before. We calculate the network sizes, determine the masks, we sort the networks in reverse order, and we start assigning network addresses. So let me start with calculating the network size. If we go back to our topology, okay, we see that the largest network was local area network A with 42 nodes. So we're going to go into our table, and if we add 2 to that, we get a total of 44 IP addresses that we need. Now, as I said before, our network is going to have to contain more IP addresses than we're currently needing in order to fill the space to get to a binary boundary, which in this case is going to be, the next highest boundary is 64. Subnet mask 256 minus the size or the IP count in that octet, and that will give us a 192 on whatever interface is connected to LAN A. Now I'm going to skip doing the network address and the broadcast address for a moment, and I'm going to fill in the table for the first 3 columns. Our second biggest network, if we recall correctly, let's go back to the diagram, is going to be LAN number C with 24 nodes. And when we go and fill this in, that means we need a total of 26 IP addresses. In this case, the binary boundary will only be 32. That's the next higher power of 2 above 26. Our subnet mask on this interface is going to have a mask that's different than our first one, hence the concept of variable length subnet masking. Our last interface on the local area networks had 11 nodes, which means we need 13 IP addresses. The binary boundary size for that's going to be 16. And once again, we calculate our subnet mask as 255 minus the size, 16. And here we have 3 different subnet masks. And again, the concept, variable length subnet masking. Now we've got 3 wide area networks that each need a total of 4 IP addresses. The 2 router interfaces, the network address, and the broadcast address. So we need a total of 4 IP addresses on the first wide area network. Now this is one of those cases where our binary size and our node or IP count are equal. And that's okay. As long as it's a network, you don't anticipate any growth, that's fine. And so we calculate our subnet mask, and that's going to be 256 minus 4, or 252. The remaining 2 wide area networks are the same, so I'm going to go ahead and fill in the details, and got one step ahead of myself here. I started filling in here the network address column. We are going to start with the very first IP address of the block that we're issued. Notice that my table is sorted in descending order, where the top row is the biggest network and the bottom rows are my smallest network. That is so critical. I cannot say it enough times. I can do a separate video, much longer video, that explains why. But what happens if you don't do it that way? Logically, you get hosts that are on different networks and they can never talk to their router. So we've got our network address is the first IP address that we own. It's really easy to calculate the next network address. All we have to do is take the size of our first network, add in the network address of our first network, and those 2 numbers added together become the network address of the second network. If we continue that process, our third network, we combine the size of the second network with its network address. 32 and 64 produces 96. That becomes the network address of the third local area network. Likewise, to get our address for the first local area network, we take the size of the third network, we add its network address, we come up with 112. That becomes the network address for our first wide area network. And that logic continues on until we fill in our network addressing. Now, a very common practice is that oftentimes a network engineer will make the router on the network the very first usable address on that network. None of these are usable because they're the network address. But with that logic, if they chose that, we would have 10.1.1.1, .65, .97, .113, .117, and .121 as the address for the router. Although I've also seen people use the last usable address on the network. So let's go ahead and find out our broadcast address, which, even though it's not usable, we just subtract 1, and that would be the last address on the network. Finding the broadcast address is actually quite easy. All we have to do is look at the network address of the next higher network and subtract 1. So our broadcast address for the first network is 63, which is 1 less than 64. We get 95, 1 less than 96. We get 111. We'll get 115. We will get 119. The last one, basically, for this one, we don't have another network. If we did, it would start at 124, 120 plus 4. We subtract 1, and we get 10.1.1.123. And now, basically, in this table, all of the IP addresses in between the network address and the broadcast address are assignable as node addresses. And we have allocated IP addresses in a way that doesn't waste too many, and life is good. Variable length subnet masking. So basically, in summary, what we discovered is that the steps for doing VLSM is to calculate your network sizes and making sure that you add 2 IPs for the reserved network and broadcast. You add, you round up to the nearest binary boundary. You take 256 and you subtract that number. That gets your subnet mask. And I can't tell you this enough. You sort your networks by the largest size first, and then you begin your addressing sequentially from biggest to lowest. My name is Dave Seamus. I hope this presentation has been helpful. This is actually part of the Cisco CCNA preparation program. That's at Pierce College in Woodland Hills in the Los Angeles area. And maybe someday I'll see you either virtually or face-to-face in a class. I hope all is well.